Hello, welcome to today's topic, which is power series. Okay, so we take the ANs to be a sequence, our x is a variable, and in part 2 we'll use c being a real number. And a power series in x is this infinite series here. Okay, so we have sum from n equals 0 to infinity of an x to the n. So the a's here are the coefficients of an infinite series in x, and this is a power series. I'll say this number 1 here is the simplest form. The more general form is a power series in x centered at c, and here we can see instead of just an x we have an x minus c in each of the terms, and the a's are still the coefficients. So that is the definition of a power series. So we take a couple of quick simple examples. Here is about the simplest example I think we could have. Here all the coefficients are 1, and this is centered at 0, there's no minus term here. So it's simply 1 plus x squared plus x cubed plus x to the 4, and so on and so on and so on. Here we have a minus 1 to the n, so it alternates, it'll go plus minus, and the coefficient this time will be n over 3 to the n. And now it's no longer centered at 0 here, we've got the x minus 2 term. So the first few terms here, well, the first term is 0 because the n will be 0 here. And then we divide by 3 to the n each time. So we get the powers of 3 in the denominator here. We could simplify here. You see we have 3 over 27. But I actually like leaving the terms as they are. That way you can see where the pattern comes from. It's a little easier to spot the pattern there. So we'll leave that. And we'll say that that is centered at 2. Okay, so really what we're interested in with our power series is when and where they converge. And so we take this general power series centered at C. Then there's 3 possibilities for when and where these things converge. The first possibility is that the series only converges at C. Okay, and it should be pretty obvious if we plug in x equals c into here. In fact, this term goes to 0. So it will definitely converge there. No matter what happens everywhere else, it will definitely converge at C no matter what. The next possibility is that there's some sort of finite range for which this converges. We say there's an r greater than 0, such that the series converges for all x between c minus r and c plus r. So in other words, we go r either side of the c, and it will converge in there, but it will diverge for anything less than c minus r, and any x greater than c plus r. So that would be some sort of finite range. And then the final possibility is simply that the series always converges for all x. Okay, so those are our 3 possibilities. And the r we refer to here, we'll talk about a bit more here. The number r here is called the radius of convergence. Okay, that distance either side. Now, when it just converges at x equals c, the radius of convergence is 0, in other words, r equals 0. And when it converges for all x, we say it has an infinite radius of convergence, in other words, r equals infinity. And the interval of convergence is the set of all values for which it converges. So that's that range, either 0 or infinite, or that finite range. Okay, so that's quite a lot to take in. I think we should probably take an example now. So we want to find the interval and radius of convergence of this power series. Just a quick reminder, if we're going to do this, we're going to use the ratio test. So hopefully you remember the ratio test from here. Here it is. The limit then goes to infinity of the an plus 1 over an, this ratio, equals L. And remember, we're looking for where the L is less than 1. It gives us convergence. When L is greater than 1, it tells us it diverges. When L equals 1, well, then we don't know. We'll see where that comes into play in a little while. Okay, so say we're taking the ratio test. So here is that ratio, the an plus 1 over an. Okay, and we plug it all in here. Plug in n plus 1 in the numerator here and just add in the denominator. And then hopefully if we've mastered the ratio test, this shouldn't be too hard. Remember, we're going to flip the denominator, take the reciprocal, and we're going to get something like this. We can throw away the minus 1s because we're in the absolute values. And then here we can simplify. If we've got the x minus 3 to the n plus 1 and x minus 3 to the n. Most of those cancel out, some of the n's. So we're just left with x minus 3. We can take the n over n plus 1 outside the absolute value signs. and we're just left with this. Okay, and we want to know for which values does this converge. Well, as n goes to infinity, the n over n plus 1 goes to 1. So we're just left with the absolute value of x minus 3. And remember, we want that to be less than 1. Now that was the point of the ratio test, is when this is less than 1, then the series converges. Well, saying that x minus 3 is less than 1, just a quick reminder of how we can do that. You can't remember. It's another way of saying that is that x minus 3 is greater than negative 1, but less than 1. And if we add 3 to both sides of that, we get that x must be between 2 and 4. So that gives us pretty much our interval of convergence. However, there's one more thing we have to do. Remember, the ratio test said that if L equals 1, then it's inconclusive. It doesn't tell us anything. And these two endpoints, the 2 and the 4 here, are where x equals 1. So that means that we know it diverges for x less than 2 and greater than 4. We know it converges for x between 2 and 4. But we don't actually know what it does at 2 and 4. Okay, well, so we have to check those. We can quickly pop 2 back into the original formula. And I'll do the algebra pretty quickly, but if we plug 2 into this original series here, in fact our series just becomes sum from n equals 1 to infinity of 1 over n, which we know diverges, that's a harmonic series. And similarly, we plug 4 in here. In fact, we get something slightly different. We get the sum from n equals 1 to infinity of minus 1 to the n over n, which is an alternating series, and the terms are going to 0, therefore this is convergent. So we know that it diverges at 2 and converges at 4, so our final interval of convergence is 2 to 4 here, but you'll notice we're open at this end and closed at this end. And then the very final thing we need is that the radius is 1. If you're not sure about the radius, a nice easy way of thinking about it is always half of the interval. So the interval goes from 2 to 4, so the interval is 2, the radius will be half of that. That's how far away from 3 on either side we are. Okay, so it was quite involved, but that's the interval and radius of convergence of this series. Let's take one more example, and this one actually turns out to be a little easier. Minus 1 to the n, so it's alternating again, and we have n factorial x plus 2 to the n. Notice this one is now centered at negative 2. Our previous example was centered at 3. This one is centered at negative 2. And so let's take the ratio test again. Again, we get this ratio, the n plus 1 over the nth term. Plug n plus 1 in here, plug n in. Simplify. And we're down to this n plus 1 factorial over n factorial. We've seen this a couple of times now. Hopefully we know that that goes to simply n plus 1. So we have the limit as n goes to infinity of n plus 1 multiplied by the absolute value of x minus 2. And we need to say, when is that less than 1? Well, it should be clear that this limit on the outside of the x plus 2 here is actually just going to infinity. Okay, which is greater than 1. So it's tempting to say never. However, if we plug in x equals negative 2, we do get that it is 0 here, therefore it converges. But that's the only point at which it converges. Remember, that was one of our possibilities, that it only converges at one point. And so we can say that it converges at x equals negative 2 only. You can say the radius is 0. Okay, so that is the interval and radius of convergence of that series. That's about it for power series now. Next couple of classes we'll actually look at how we can take functions to be series, and that's why this is so important. For the time being, this is just some of our techniques for finding the interval and radius of a power series.